Hi everyone, here we are to our second week of the online PChem class. I hope you had a nice weekend and I hope that last week went well for you. I also hope that you're asking your questions on the discussion boards and that you're coming to office hours and that your preparations for your lab reports are all going well. Make sure that you check the due dates for all of those things. And let's go ahead and get started here on the second lecture of Chapter 9. First off, just a reminder, I'm planning on having the pre-class discussion on the discussion boards. So I'm not gonna do the pre-class on the videos because I post these videos before the pre-classes are due. So go ahead, if you weren't able to do the pre-class or if you had any questions about it, then go ahead and post all your questions there on the discussion board. Okay, well, we'll review what we talked about last time. Then I'd like to talk to you about the lever rule because of its similarity to the physics of a lever. We'll get to colligative properties, which means when we have a mixture, that's going to raise or lower the boiling or freezing point. Activities apply to non-ideal solutions, and we need activity coefficients to calculate those. And then we'll see how to get the chemical equilibrium constants and how that relates to the free energy, etc. Last time we saw Raoult's law, which applied to ideal solutions. And remember, in ideal solutions, the delta H of mixing equaled 0. And Raoult's law states that the vapor pressure above the mixture of component A is going to be equal to the mole fraction of that component within the liquid multiplied times what the vapor pressure of A would have been in the pure substance. So this is X in the liquid, and remember Y is in the vapor. I thought of a silly, dumb way to remember which refers to which. It's so dumb, but I'll just go ahead and tell it to you anyway. X is for liquid and Y is for vapor. Vapor. Notice that I accentuate the ye sound in the word vapor. So that's how I remember. I know it's dumb, but but it helps me. Yeah, and remember this is the vapor pressure of pure A. Okay, what else did we see? We also saw how the chemical potential was calculated for a substance in a mixture, and that was for component I in solution. So let's say we have a number of different components in the solution, I, J, K, etc., equals what that chemical potential would have been in the pure substance plus RT log mole fraction of I. This is going to be an expression that comes in handy when we deal with activities and non-ideal solutions a little bit later today. We also saw the free energy and entropy of mixing, and that equation was delta S of mixing is the sum, and then I have NR out here, sum of all the different components, xi log xi, and then delta G of mixing just equaled negative T delta S of mixing for ideal solution. Okay? Then we also saw the calculations involving the liquid and vapor phases of a binary mixture. And if you need to, you can go review those equations for your homework or any other purpose. First, I'd like to introduce you to this idea of a PZ phase diagram. So this is a new type of phase diagram. Instead of pressure temperature, this is pressure mole fraction, okay? If X was the mole fraction of liquid and Y is the mole fraction of vapor, it's supposed to be Y, then Z is total mole fraction. Okay? That is the mole fraction of the liquid and vapor states combined together. Let's take a look at this plot I'm showing you here. This blue curve is labeled liquid, and that's because it's a plot of XA in a binary mixture, so binary, so that means that there's two components, A and B. And then there's also this green curve here that will tell us the pressure of the system as a function of the mole fraction in the vapor state. Okay? So the system is going to be existing at a particular pressure, and this point here tells us what that pressure would be for a given mole fraction in the liquid. But as soon as we know that pressure, then we can immediately figure out what's going to be the mole fraction in the vapor state up above that mixture. And that's what this phase diagram tells us. It's going to allow us to determine what's going to be the proportions of the different components of the mixture in the vapor and the liquid phase at the same time. So how do we calculate Z for a given component A? Well, it's going to be the total number of moles of A divided by the total number of moles in the entire system. And the book tells us this is just the number of moles of A in the liquid state plus the number of moles of A in the vapor state divided by number of moles of A in the liquid plus the number of moles of A in the vapor plus number of moles of B in the liquid plus number of moles of B in the vapor. And remember, this is a binary mixture, so there's only two components here. Next, I want to talk to you about the lever rule, because the lever rule is going to allow us to draw where Z is on that PZ phase diagram that you saw in the last few slides. So I'm going to try to draw at least a crude rendition of that PZ phase diagram. Got our 2 points, PB star, PA star. I'm going to label ZA down here. Goes from 0 to 1. Okay, and then I'm going to use two different colors to represent consistently like I did on the last slide. There's the liquid, and then here's the vapor. Okay. So let's say I create a system like this, consisting of a binary mixture, and I figure out what's the pressure of the system. And I say, okay, there it is right there. That's going to have a certain mole fraction in the liquid state, and it's going to have a certain mole fraction in the vapor state. What about Z? I'm going to tell you right now that Z is going to exist somewhere in between those. And for the sake of argument, let's just say that it's right there. But how do we find exactly where that one is? Before I tell you that, I'm just going to accentuate the fact that XA and YA are different numbers. And remember, this line here is called the tie line, and Z exists somewhere on there. So let's zoom in on that spot. I'm going to redraw that little area of the tie line. Kind of zoomed in over here. Okay. I'm going to call this span of distance J, and I'm going to call this span of distance K. Remember, up here we have the liquid And down here, we have the vapor. Hopefully you're beginning to see why this is called the lever rule. Do you see how this sort of resembles a lever in a physics problem, where maybe we have a mass of mass XA over there, and we have a mass of YA right over there. Where do we put the fulcrum? Remember, the fulcrum is the place where we can balance a lever with a weight on either side. So where do we put this fulcrum to balance it? And it turns out that the same equations will describe these mixtures of liquids and physical levers. And I'm going to tell you the result right now. The total mole fraction of A minus the liquid mole fraction times the number of moles total in the liquid state are going to be equal to the mole fraction in the vapor minus total mole fraction times the number of moles in the vapor. And this is it. This is the lever rule. And if you ever needed to find z from x and y, or if you ever needed to find the number of moles of liquid, or any of these unknowns, you would just use this algebraic equation to do so.